Hi, my name is Stephen Neuendorffer, and I'm going to be talking about architecting out-of-tree LLVM projects using CMake. So in 2015, there was a great tutorial that talked about how to take an LLVM pass and build it out of tree, and then link it into LLVM afterwards. And there's also a great tutorial here if you're interested in LLVM passes. However, what we see is that there's actually many more complex projects now, and many of these projects are in tree, so like Clang and Flang, and the runtime projects. But some of them are also out of tree, like the LLVM incubator projects, Torch MLIR and Circuit. So the goal of this talk is really to try to capture some of the lessons we've learned from these out of tree projects and to document how to best practices for future projects and to get new projects started more easily. So as a disclaimer, this is really heavily biased towards my personal experience and MLIR in particular. So I definitely love to hear from people who have other ideas about how to best work with other kinds of projects. So what's the context? So in the beginning, there was LLVM, and many other projects have sort of started to exist in tree in the mono repo that depend on LLVM. And all of this is configured using CMake. We also have our out-of-tree projects like Circuit and Torch MLIR and others like Onyx MLIR. And a lot of times, if you're like me, maybe you're in the position where you have an out-of-tree project and you need to depend on all of this. So you need to take into account things that are changing in LLVM and MLIR and the various out-of-tree projects and to try to integrate them all together into your cool idea. And there's a couple of different ways to actually architect this. If you're familiar with the way LLVM projects have been built for a long time, usually we deal with a monolithic build with our sources in tree, so like Clang and Flang. And the real problem here is that configuring is quite slow because we have to configure everything in LLVM at the same time. And we also need the LLVM sources. But it's relatively easy to get started with this kind of build process. There are also ways of taking your source code and getting it out of tree, but still having that monolithic build that has a slow configure. So if you're able to parallelize your compilation, then a lot of times compilation can be sped up quite a bit. But configuring often is still a bottleneck because it can't be parallelized very easily today. So what I hope to show you in this talk is a lot of tricks for how to handle out-of-tree sources and also componentizing your build so that you can have configuration for your components done fast. They don't have to rely on LLVM. And you also only need the LLVM headers in order to do this. And although this is a little bit more complex, hopefully after this talk, you'll understand how to do it and find out that it's not actually that hard to get started. So in doing this, I think there's a bunch of challenges. So first off, we need to get our source. How do we get our sources and how do we get LLVM? Then I'm going to talk about configuring and building LLVM by itself. Before I talk about building and configuring your project that depends on LLVM. And lastly, I'll leave you with a few neat tricks that I think will be able to make your life easier in building out-of-tree projects. So how do we manage our sources? In the LLVM incubator projects, most of the time we focus on using Git submodules to manage our source code. And in this case, we use special Git commands related to submodules that allow us to refer to LLVM and the LLVM sources and to bring them into our tree. And the great thing is that this is standard infrastructure. We're just using existing Git commands. And Git will automatically check out the right version of LLVM along with your project when somebody checks out your project from GitHub, for instance. The big downside of Git submodules is that it becomes more complex to use Git. There's a different set of commands that you have to understand. And certain Git use cases like merge commits become a little bit more complex. The other problem I've shown here on the right, where you can end up with multiple copies of LLVM. So for instance, if you have a project and your project depends on LLVM, but it also depends on Circuit and the Torch MLIR incubators, then you can end up with 3 different copies of LLVM because of the daemon dependence between different projects. Another option that some projects use, like Onyx MLIR, is to just have a checkout script. And what this checkout script does is it sort of documents in an executable format the version of LLVM that you want to use for your project. The downside of this is it tends to be non-standard. It's just a script. And so every project kind of does this in a slightly different way. It also requires more input from a user or integration with your CI flow in order to make sure that the right version of LLVM gets downloaded. But the advantage of it is that it's a little bit easier to manage these kinds of daemon dependencies and to keep only one version of LLVM in your source tree. In my opinion, neither one of these is a very great solution, but we have to pick one of them. So if you have a better idea for how to approach this, I'd love to hear from you. Another thing I'd recommend when building LLVM is to try to use shared libraries. This really helps to reduce the size of the installed code and to also reduce the build time overall, since we don't have to link all of our executables individually. The big downside is that it's not supported on Windows, and there is some increased runtime overhead from the shared library boundary. Now, there are two basic ways of configuring this in LLVM. One is around the build shared libs option to CMake. So what this does is it compiles every target library into a separate shared library. And this tends to be pretty good for development, but it's not really recommended for deployment since we aren't really architecting these shared libraries very carefully to have them expose a standardized interface. This means that you really don't want to install these shared libraries in your system, for instance. On the other hand, the other option is to use LLVM.so. So this is what we call an aggregate library. It aggregates a lot of the LLVM static libraries into a single large DLL that you can then link your project against. This is a little bit more complex because it requires some specialized LLVM infrastructure in CMake. But it is good for development and deployment. So it's very common to have a distribution that has LLVM.so and to allow you to link against that DLL. So when you do go to add your targets, especially in out-of-tree project, you should be aware that there's a couple of different CMake functions that you can call that are in the LLVM project. The sort of most basic one is called LLVM add library, and this creates a library that can depend on LLVM.so. This is useful for both in-tree targets and out-of-tree targets. So you'll see this used in LLVM internally, but this is also the best thing to use if you're out-of-tree. It also uses a function called LLVM update compile flags, and what update compile flags does is it makes sure that all of the standard compilation options for an LLVM library are set more or less the same way. There are two other functions that are used quite extensively in LLVM, but these aren't really useful for out-of-tree code. One is add LLVM library that creates a library that's part of LLVM and will get installed along with the rest of LLVM. And another is add LLVM component library. So it creates a library that is going to contribute to LLVM.so. And obviously you don't want to use this if you're out of tree because it's very difficult to add things to LLVM.so in that situation. So to look at this in a little bit more detail, here's an example of some CMake that comes out of the LLVM tree to define two component libraries, LLVM demangle and LLVM support. And in this case, it turns out that LLVM support actually depends on LLVM demangle. And so it has a line that includes link components with demangle. It's the name of the library just without the LLVM prefix. We can imagine an out-of-tree project that also defines its own library with some source code. And here, this library is going to depend on LLVM support, so it also has a link components line. So by default, if you configure with LLVM build LLVM dilib equals off in CMake, then what you'll get is three static libraries. libmytarget.a that depends on LLVM support, and LLVM support that depends on LLVM demangle. Now, if we set the right options in order to compile and link with liblvm.so, then without changing any of the CMake declarations, we can get a very different build process. So in this case, we have a static library for our project, but the static library links against liblvm.so, which contains all the code from demangle and support libraries. One thing that's been in progress is to come up with a way to generalize the liblvm.so mechanism. One of the things that has to happen in the case of liblvm.so is that we need to switch back and forth how the build process happens. And this is somewhat complicated in the CMake files. So what the aggregate library mechanism allows us to do is to specify our project in this way more easily And this is built into MLIR right now. So for instance, if you call add MLIR library with the enable aggregation line, then this declares that your library is something that can be aggregated into a larger aggregate. And the add MLIR aggregate function allows you to embed libraries that have been previously declared with add MLIR library, as shown on the right over here. So today this is used to build the C API libraries in MLIR, but in the future this will probably be used to build libmlir.so, and hopefully we can generalize this to other LLVM incubator projects. So next up, we're going to talk about how do we install LLVM. So one option is called LLVM install toolchain only. And this option tends to give you pretty coarse-grained control over what components of LLVM actually get installed when you run make install or ninja install. So the goal here is generally to reduce the installation to only what is needed. So we don't need everything from the build tree. We only need the things that are going to be used at runtime. The big downside of this option is that it's hard to control what we actually want to install directly. And in particular, there's not really a way that I found to install either the headers or the test infrastructure using this mechanism. So generally speaking, I would discourage using this. Instead, I would recommend using LLVM distribution components as an option. And this gives much finer grained control over what gets installed. The big advantage is that we can install things like the headers and the test infrastructure from LLVM along with your LLVM build, so that we can then make use of them when we're doing an out-of-tree componentized build. The option down here looks something like this. So with LLVM distribution components, most libraries and tools are things that you can specify as a component in this line and have them installed along with your LLVM build. In addition, these sort of pseudo targets are useful for representing different components, like the export of information in CMake that we'll talk a little bit more about next, LibLLVM, and along with the headers that you're going to need to compile against LibLLVM. So now let's talk about a few different ways that we can architect our build in a little bit more detail. So earlier I talked about an in-tree source and a monolithic build. So in that case, we might have our Git mono repo checked out, and we've started adding our project inside the LLVM tools subdirectory. And in this case, it's very easy to configure and build your project along with LLVM by specifying LLVM enable projects and adding your project to the list of projects that get compiled. When we build, we end up with a build hierarchy that's actually a little bit different from the original source hierarchy, because this is the way CMake's view of the directory structure is a little bit different. In this case, we're pointing CMake at LLVM as the top level of our build hierarchy, and all of the LLVM projects exist at the next level of build hierarchy, like MLIR and Clang and your project. If we have an out-of-tree source but a monolithic build, then that basically allows us to re-architect our source code so that we can have our project in a separate Git repository. It doesn't have to be polluted as a fork of the LLVM repository. And in this case, the build process is very similar. We just have to specify some additional options that tell CMake where to find our out-of-tree project. I skipped the slide. So if we have a componentized build out of tree, our source files are again going to stay the same. But in this case, we can execute two separate builds. First, we can build LLVM with one run of CMake and one run of Ninja or Make. And then later, we can come back and build our project. This makes use of information that is exported from LLVM into our build in order to execute concurrent, to configure our project. One advantage of this process is that we can also install LLVM into a location, and our project can also be built against an installed version of LLVM. So the key idea that makes this work is a mechanism that's built into CMake called find package. And the basic idea is that from one build, we can export information in a standard way that's used by another build. So, for instance, in LLVM, there is information in LLVM and MLIR in these files that is then configured at build time to export information into the build or install tree associated with the files on the right. So libcmake LLVM, LLVM config, and MLIR config are the important files to think about. And then when we are building our project, we can import this information using find package. So what's required in CMake is just the line find package that with the name of the package. In this case, because we're importing LLVM, we're going to look for the LLVM config.cmake file. And we're using the config mechanism to find that. CMake actually supports a number of different find package protocols to find this information, but we're using the config mechanism. And this is required. So if we can't find LLVM, then we just want to fail immediately and not bother going through the rest of our configuration flow. In some cases, you might also have to specify an additional environment variable or CMake configuration variable in order to help CMake to find the right directories for these files. Note that the directory we're specifying here is actually the directory that directly contains the config file. So in our project, when we're actually exporting this information, this happens in CMake. And the key thing to recognize is that this actually needs to happen twice. We need to generate a different configuration depending on whether we're exporting information about a build directory or an install directory. So for more information, you can see this file in the MLIR source tree. But basically, it boils down to use of the CMake configure file and export options. So the configure file function takes a template, in this case, a CMake.in file, and generates the config.cmake from it. And export targets generates a file that has all of the targets in our project based on all of the information that's in our CMake lists. So for the build directory, we just need two functions to be called. For an install directory, we need to first configure the file and then install that file into our install tree, and then call a different function, in this case, install with the export option that's going to generate the targets file for an install directory. When we go ahead to import that into a new project, then it's simply a matter of calling find project. And depending on whether we have a build directory and install directory, we just point to the right config file. One big advantage of this is that we can now write our CMake targets the same way, whether we're doing a monolithic build or we're doing an exported build, because we're importing all of the information about the targets from the project that we're importing. So if you actually have an existing project and you want to be able to, that's built into LLVM, and you want to be able to run it out of tree, it's actually a relatively simple process to make that happen. Here's a little template that you can paste inside your top-level CMake lists file that checks to see whether your project is actually running in the LLVM build or it's running out of the LLVM build. And if you're running out of the LLVM build, you're a componentized build, then it will use find package to get information from LLVM. In addition, there's a few other files that you probably want to import from LLVM. So for instance, include handle LLVM options is very important because it allows your project to take most of the standard LLVM CMake options and handle them in basically the same way. In MLIR, if you are building an out-of-tree project based off of MLIR, there's actually a really great project template that is in the MLIR example standalone directory. And this is a great thing to copy. Instead of starting your project from scratch based on MLIR, you can just copy this and change the names and get your project up and running really quickly with most of the CMake boilerplate taken care of for you. This project is also very useful in tree because it allows us to test the export of information from our build from MLIR into the another build. So if you enable LLVM build examples, then you can run this rule, check LLVM example standalone, in order to build the standalone example in your MLIR build. Next, I'm going to talk about the MLIR Python bindings. So we think this is a very general mechanism that will be able to be used for lots of out-of-tree projects and is being currently prototyped inside the Torch MLIR incubator. The key thing to recognize when we're building Python bindings is that it's actually quite tricky to build and link them. In LLVM, we normally compile without RTTI or exceptions in C++, whereas those are required when you're using PyBind 11 to generate your Python binding. So in order to make this simpler, we also only expose a C API through PyBind. PyBind is capable of leveraging C++ and exporting a C++ API through into Python, but this turns out to be a lot less portable. And in any event, it's often useful to have a C API defined so that we can enable other language bindings. Another important thing to remember when we're building Python bindings is that we actually have to be very careful about the libraries that they depend on. So any library that your Python binding is dependent on has to be globally unique. So if we follow these rules, then it becomes relatively easy to create a Python extension that consists of both a dynamically linked library that's dynamically linked into Python and Python source code. So in CMake, there now exists a number of functions in the MLIR project in order to help define these Python extensions and get them properly linked and built. There's basically two different parts of this. One is a set of functions that are used to declare your extensions, and I'll talk a little bit about what those functions are, and other functions that are required in order to actually build your extensions together and to link them properly. So depending on the kind of the type of extension, there's a few different options here. If you just have Python sources, then you can use the first function here. If you have a Python extension that also includes C++ code, it's going to create a .so file. In that case, you want to use the second function here. And the third form is actually really useful if you have an entire MLIR dialect and you want to export it into a Python binding. Then you can just point this function at the right table gen file, and it will automatically generate the right Python and DLL Python extension for exporting that into Python. When it comes to actually building this, we have to take all of our the C++ code that all of our extensions are going to link against and compile them into a single .so library that is something that we can install along with our Python extension. So to actually build and define that, we use the add MLIR Python common C API library. It's quite a mouthful, but it actually does quite a lot to link all of the dependencies of all of our extensions together. And then add MLIR Python modules actually goes and builds our extensions for us. Lastly, note that you do need to enable the bindings in Python, both in LLVM and also in MLIR, in order to make this mechanism work. So here's an example of how you might use these functions. So this is again taken from that standalone example in MLIR. So to begin with, in the lower left here, there's a number of different extensions. In fact, there's an extension that is a dialect extension that is declared, and an extension which is a C++ extension that primarily consists of C++ sources. And both of these are aggregated within a tree of extensions. So in this case, at the top level, there's a Python source extension that actually doesn't contain any Python sources, but is just here to exist as a container for the other extensions that we have. So the key thing to recognize is the add to parent option, which specifies the containing extension of a particular Python extension that we're trying to build. Now, In addition to the declarations for our local project, there's also a bunch of declarations that we need to import from MLIR in order to build all of the MLIR extensions together into the same library and have them interoperate with our new extensions. So if we take all of these declarations and we then specify them in the declared sources line of our call to both add MLIR Python common C API library and add MLIR Python modules, then these will build a library of or a set of DLLs that are useful together or usable together in order to link into Python. Okay, so now let's start looking at a number of tricks that you can use to make building your projects even easier. One thing that we use a lot is the CMake external projects option. And so in this case, you might be aware that there are a few different ways in CMake of having design hierarchy. So normally we use this add subdirectory function to describe how one directory in your source tree relates to other directories in your source tree. And generally speaking, this is nice because it allows us to show the fine-grained dependencies between different targets in our project. And also all of the information from the higher level directories in our project gets pushed into the lower subdirectories of our project. It's also possible in CMake to combine add subdirectory with hierarchical projects. So for instance, we can sprinkle a new project declaration using the project function anywhere in our source hierarchy. And in this case, it's very similar. Most of the information transfers from the top level directories into the subdirectories, but some variables are reset where the project function is called. But neither of these are very useful for a componentized build. In a componentized build, we prefer to use the external project add command. And what this does is it really executes a separate run of CMake for each directory. So the assumption here is that we actually don't want to take information from higher level subdirectories and pass them into lower subdirectories, unless we explicitly pass that as an option to external project add. So this is very good if we have our project and we want to be able to compile a number of different sub-projects like LLVM or Circuit or Torch MLIR. We can say how our project depends on these sub-projects, and we can say how these sub-projects also depend on each other. And each of these sub-projects will be built completely independently as using the componentized build process. And the information that's passed to them will primarily be using the CMake export mechanism to get information from one build into another. We can also specify coarse-grained dependencies using the external project add command so that we can make sure that we always build LLVM first before it builds Circuit and Torch MLIR. And all of these have to be built before our project libraries are built. So I really recommend you read the documentation on this. It's a very useful mechanism we found. Another thing that all the LLVM incubator projects are using pretty heavily is GitHub Actions. And we've been applying some techniques that try to speed up the builds using GitHub Actions. And here the big problem is that the default runners in the GitHub Actions process are actually quite limited, and rebuilding LLVM takes at least an hour on the free runners unless you're providing your own build machines. So the best solution that we found so far is to use the action cache that's built into GitHub Actions. So here's a link to the documentation and also a link to the Circuit build and test YAML flow so you can see how we use it. This still isn't a perfect solution, so even when LLVM is not being rebuilt, satisfying a cache hit and copying data into the build environment still takes several minutes. And there's a rather small limit on the size of the overall cache, so you might get one or two LLVM builds in the cache, but managing the cache itself can sometimes be tricky. So I think in the future, probably a better way forward is to use more GitHub Actions rules that are capable of publishing Docker images, and to use Docker images to manage the parts of our system that we want to rebuild. This is going to be a little bit more complex, but fortunately, Onyx MLIR has been making some progress in building a Docker-based flow. My last trick that I'll tell you about is that we can also use the export mechanism that I talked about to be able to separate our tests from builds. And so this is actually useful in a number of different cases. So for instance, one thing that's not commonly done in LLVM is to run all of the lit tests on an installed area. So today, when we install a distribution, it's sometimes quite difficult to test that. Ideally, we'd like to run all of the existing LLVM tests on it, but it's very difficult to reuse those tests today. Another case that we often run into is that we're doing a cross build. So we want to cross build on a server and then move the installation onto an embedded processor where we're then going to run the tests. But a lot of times on an embedded processor, it's impractical to build LLVM. It just takes too long, or maybe it doesn't build at all. So the solution that we found is to basically make the test directory a separate CMake project. So because it has a project line, it can exist at the top level of the CMake hierarchy. And then we can detect whether or not we have all of the information from the outer project by a pretty simple check. So in this case, if not, proj binary dir. And if we don't have that information already, so we're not in an in-tree build, then we can call find package to import all of the information from the build into our tests and run the tests. So down here, you can see two different lines. First, we can use CMake to build the project and install it. And then we can use CMake again to just point at the project test directory as the top level, and then use the exported information in the libcmake proj directory. So we find this to be really useful, and it sped up a lot of our cross development. So in conclusion, we're really looking to see a lot more robust projects with LLVM and MLIR, and hopefully this talk has given you some the ability to be able to more easily get your project started. And if you have other tricks, we'd love to hear about them so that we can pass along best practices throughout the community. So the next steps, I think, are to actually take a lot of this information and get it into the documentation. Some of it is there, but some of it is not. And to also see if we can leverage more of the work that's going on with the way the runtime builds are being managed, which makes use of some of these tricks like external project add, for instance. We also want to take the aggregate infrastructure that's been prototyped and export it into more uses, like rebuilding libmlir.so and also enabling similar mechanisms for the other LLVM incubator projects. So I definitely like to thank quite a few people who contributed to this this presentation, either directly or by teaching me interesting things about CMake. So thanks a lot to all of you, and have a good day.
Hi, everyone. Thanks for watching the program, the pre-recorded session. I think now we're live. I've never done this before, so we'll see how this goes. We do have the Pigeonhole questions available, and there's one person who has made a comment that I guess I'll just read. And that's Jacob, or sorry, I guess we're not saying names. In LLPC, we do full nightly builds, and then CI runs one incremental build using the latest nightly builds. This is working pretty well and gives full historical images for bisections for free. I don't know that there was a question in there. If there is, feel free to speak up. Otherwise, maybe Stephen can riff on CIs.
Definitely having some better infrastructure for how we manage multiple builds and incremental builds is kind of an interesting piece. I was kind of discussing this with Stella a little bit earlier. Maybe using more of the packaging mechanisms to implement to be able to separate out the LLVM build into multiple parts. So you build LLVM and then you can build the individual components afterwards, and manage the dependencies using more of the using a packaging mechanism as opposed to just using the CMake mechanism where you still have to have all of the sources together and configure things in CMake.
Yeah, I think that there's a lot of different approaches in the community based on how source biased you are or packaging biased you are, and I'm not sure what the right answers there are. I wish we had better facilities for all of it.
Yeah. The other thing we were talking about beforehand was how difficult it is in general to have the DLL builds come out correctly because LLVM wasn't really architected from the beginning to have very well-defined DLL boundaries. I don't know if you maybe wanted to comment on that, Stella, and see what the things you've been thinking about.
Yeah, comment, rant, something. I think that the indication for me that there's significant room for improvement here, for example, is like in your slides where you mentioned that none of this works on Windows. Some of that is Windowsisms, which we all struggle with, but the rest of it is that Windows does enforce a layering of DLLs that is actually what works for POSIX too. And the fact that we aren't supporting that is actually hiding a lot of layering bugs when you try to actually put these projects together. So I've seen this before on C++ projects, kind of, unless you are treating your shared libraries as part of your API that you're layering well and intentionally, you end up with ODR issues, you end up with mismatched imports, exports, and you end up without anchoring things in an owning shared library. And we've got all of those problems happily. So I know on the MLIR side, we're tackling a long tail of weak linkage issues where we're not anchoring things to the right shared library. And once we fix that, then I think we can actually better support multi-shared library builds. But right now it's pretty broken, to the point that I just say that MLIR specifically does not support C++ dynamic linkage. It's a lot of people are having problems with that.
Well, it definitely seems like the Python extension mechanisms that you built are definitely a good step in the right direction there, and at least helps to solve some of the problems. So,
yeah, the next step from there is kind of a big one though, which is that in order to make C++ link reliably across shared library boundaries, you need some more discipline and decisions than we've historically applied to this area. So I've solved the problem by not linking across C++ bound or doing C++ linkage across library boundaries, which happens to also happily be the right thing for Python, which wants hermetic distributions. So doesn't help anyone else though.
Thanks a lot, everyone, and feel free to reach out if you have ideas in this area. I'd love to talk to you.